Thank you very much indeed. I'm going to talk about the Grothendieck inequality in quantum mechanics and harmonic analysis. And quantum mechanics I will be using d-dimensional systems with a Hilbert space HD. And then I have a vector, which I have a column, and these vectors have a constant length, which I take it normalized to 1. And when I have unitary evolution in that system, this preserves the length. In other words, if I apply a unitary operator on this column, the length of this is equal to 1, and that means that the probability is conserved. Now, I'm not sure, because most of you are mathematicians, if you are familiar with the concept of mixed states, that means instead of having one vector, take many orthogonal vectors with probabilities. Von Neumann did this, and actually he did it also in game theory. Instead of having one player, a set of players with probabilities. And that's very important in game theory as well. So in mixed states, you represent this with some matrix. These are the vectors, orthogonal vectors with probabilities. And then the trace is equal to 1, and the unitary evolution is written like this. And the trace is equal to 1, and that means that the probability is conserved. But there are a lot of systems which are called open systems, and there, an example is when you have amplification or damping, where that vector, the length, changes with time. If it is amplified, the length becomes very large. If it is damping, it goes very small. And this has been studied extensively in the literature, and the methodology for this was usually to take the tensor product of your system with some environment and to consider some Hamiltonian there, and then you come to some models and you do some simplification and so on. And there is an enormous amount of work on this, and I call this tensor product environment. But here I will use another method where I will put an effective method where the system HD will be embedded into a bigger system, H2D, which I call the full universe. And I will do that using something called Z-Bargman representation, which I will explain when I come to it. So here, that is, I have the direct sum of my system with something outside there, and the whole thing is the whole universe. And this concept that I'm using is very different from this, because here I had tensor product, here I have a direct sum. And here the problem is that I have conservation of probability with unitary transformations in the full universe, but within the subsystem, the probability is not conserved, and the formalism allows probability current from my system to the outside world. And I have a toy model to show this, what I'm trying to do. Let's say that I have a system with n-dimensional space, the whole universe, and I have a subsystem HD, but my measurements, my equipment can only measure things in the small subsystem. I have no idea what is happening outside. And then, obviously, a vector in the full universe evolves unitarily, but I only see the projection, if P is the projector to my system, I only see the projection, I see this one, which is the projection of the vector in the full space into my system. And that is what was the unitary transformation in the universe becomes the projector times the unitary transformation in my system. So this is not the unitary transformation, it's projector times this. And you can do something like this with mixed states. But the important thing is that this view of T, which is the operator acting on the vector, in this case is not unitary, is the projection times the unitary operator, but it obeys this property. You can easily prove it. This is the diagonal elements of the projector, which are all of them less than 1, because every projector has diagonal elements which are less than 1 or equal. And this which came out of this toy model, will become the definition of what I call later scaling matrices. The scaling matrices are things which can change not only the face of a vector, but also the length of a vector. And so this will become later on the definition of my scaling matrices. And then in this case, the trace of the density matrix in the full universe is of course 1. The probability is conserved in the full universe. But I have a probability counter when I take the trace of this density matrix, which is projecting to my system. That is not necessarily 1. That is not necessarily 1. Here it is. And the trace of this, the time derivative, is the probability current, and is equal to minus the probability current which goes outside. So whatever leaves from my system, it goes in the outside world. So this is a toy model. I will make them a bit. So there is a flow of probability from my system to the rest of the space, and this is the probability current. And these open systems, why I mentioned that? Because I will link them to the Grothendieck formalism later on. But let me go to the Grothendieck formalism. What Grothendieck did, he started of what I call a classical quadratic form, which is this thing. This is a complex matrix theta, and they are scalar quantities in the unit disk. And I call it classical quadratic form precisely because they are scalar quantities, these things. And Grothendieck replaced them, the scalar quantities in the unit disk, with d vectors UR in a d-dimensional space HD in the unit ball of the space. In other words, these vectors have length less than 1. And then he proved, so I call this quantum quadratic form because it changes scalars into vectors. And then he proved that for any dimension d, this quantity, assuming that this quantity is less than 1, then this quantity is always less than what is known now as the Grothendieck complex Grothendieck constant. And the exact value of this, so the Grothendieck theorem is that when that C, the classical quadratic form, is less than 1, then this is less or equal to that number, the Grothendieck number, which is 1.4. The exact value is not known, but approximately is known that it's around 1.4. And the Grothendieck constant is a mathematical ceiling. Quantum objects cannot go more than this. And I find it very interesting, especially when that Q takes values above 1 up to kg, up to this 1.4, because this, classically, you can't have that C less than 1, greater than 1, but quantum mechanically that Q can take values greater than 1 up to this kg. So it's of special importance to go near that ceiling. And I was thinking about these ceilings, if I can give an example outside mathematics and physics. I thought Olympic Games is a ceiling of what a human being can achieve. You can't go more than that. Formula 1 is a ceiling of what the concept of a car can achieve. So this is a scene for quantum mechanics, the Grothendieck quantity. Now, you might think, oh, I'm not familiar with that quantity Q, the Grothendieck Q. In many special cases, it reduces to many well-known quantities, like Wigner functions, ambiguity functions, some other quantities that enter there in tomography using symplectic transformations and so on. So it's a very general quantity, but in many special cases are very well-known quantities. It's not out of the blue. And it's difficult to find examples with that which give the Grothendieck Q in that region above 1 up to that 1.4. And you can prove, I have proved that for all pure states, and also for some mixed states, in isolated systems, that Q is less than 1. So what I did next is I looked at these open systems, and this is why I'm looking at the open systems. Because I'm interested to find examples where that Q take values greater than 1 up to 1.4. Now I have to say that Grothendieck's initial paper used tensor products of Banach spaces. And for this reason, previous work in the quantum context, it was for multipartite entangled systems, and there is a link between Q greater than 1 and the Bell inequalities and so on. But all later mathematical work proved that you don't need tensor products at all, and there is a lot of mathematical work. And for this reason, all that I am doing is about a single quantum system with Hilbert space HD. There is no tensor product, there is no entanglement, nothing like that. And my first step will be to express this, the Grothendieck, the classical quadratic form and the quantum quadratic form as a trace of products from matrices, using something that I call rescaling and dequantization matrices. And my definition of the rescaling matrices enlarge the set of unitary matrices by introducing matrices which can change not only the length of not only the face of a vector, but also the length, to make it bigger amplification or smaller damping. And the definition of a rescaling matrices is this one. If I have a matrix Mij, I take this sum, this to be less than 1. And by the way, they form a semigroup. Yeah, obviously, because anything which has irreversible phenomena is a semigroup. There is no reversibility. So rescaling matrices have this quantity less than 1. But if I have an arbitrary matrix, I find this value. If it is greater than 1, I divide it by the matrix, and then it is a rescaling matrix. So an arbitrary matrix, by normalizing it, by putting this in the denominator, becomes a rescaling matrix. Another which I will use is the dequantization matrix. It's a special case of rescaling matrices where you have all the elements in the same row are equal to each other, and they are like this. And why I call them dequantization matrices? Because acting on vectors in HD, I get vectors in H1, dimension 1, which are effectively scalars. And if I have a superposition of vectors here, it becomes sum of numbers in here. And that's why I call them dequantization matrices. Now, I can express the classical quadratic form in terms which I gave earlier, which is this. In terms of this dequantization matrix is like this. And I can write the quantum quadratic form in terms of these rescaling matrices like this, where that V is related to this. It has these components in the S row, and that W is this written in another way. It's the matrix which has these components in the R row. So W and V is effectively this. So after I write this, the Grothendieck theorem now becomes that if C of theta, the classical quadratic form is less than 1 for all these things in the unit disk, then the quantum quadratic form is less than this Grothendieck constant, which is, as I said, 1.4. And now, approximately. Now, another thing is that if you give me an arbitrary matrix, which that C of theta is greater than 1, then I can find this, which is the supremum, and then by dividing it, that becomes less than 1. So for any matrix, I can make that, if I normalize with this, I can make this less than 1. Now it's not easy to find this because there is supremum here. When you have supremum, things become difficult. So it's not difficult, but you can find that this G of theta, you can prove that this G of theta is less or equal to D times the maximum singular value of this theta. Now there is a necessary, it's a proposition, necessary, I won't go too much into this, but not sufficient condition for if you want to get Q greater than 1, this has to be a strict inequality, and then that interval between G of theta and that quantity is very important in order to find examples where Q greater than 1. So this is necessary, but it's not sufficient. So even if you find example which obeys, it has this strict inequality, it might not be, it might not give K, it might or might not give Q greater than 1. So now I have formulated the Grothendieck theorem by saying that for any matrices, theta V and W here, because I normalize this is less than Kg. The assumption that the classical quadratic form should be less than 1 is in that denominator here. So I don't have to make any assumption now. I say that this is there. Now, and a very important point, the denominators are not invariant under unitary transformation, as you would expect in open systems. Unitary transformations are for isolated systems, for the full universe. If you have non-isolated system, an open system, then you don't have unitary transformations. They are not, the quantities are not invariant under unitary transformations. The trace, of course, is invariant, but these normalization constants are not. And now, I will explain the other bit that I need, how to embed my smaller space into a bigger space, which is the full universe. I take this matrix, it has some nice properties, regardless of this kind of work, but it has some nice properties anyway. I introduce this matrix here, where Z is a constant in the unit circle, where each column you shift upwards the previous column. So this and this Z goes at the bottom, and then you shift it upwards and so on. And then I get the D times 2D matrix, which has A of Z, this one, and then A of minus Z. And they have some important properties that I call them semi-unitary in the sense that MZ daga is 1, MZ daga MZ is a projector, and projector in some sense is one within the space where it projects. So I get this matrix, this is a D times 2D matrix, it has this property here, and P of Z is that projector, and it has D eigenvalues equal to 1, which span the space HD, and D eigenvalues equal to 0, which span the space H null D. And this is where this will be my external, physically this will be my external space, and this will be the space of my system. And by the way, the 1 minus Pz, which is projects to the null space, is equal to P of minus Z. So this is my system, this is the external system, and this is the full universe. Now, one comment that I realize I have to go very quickly in this. You can interpret if you want. Here you have, in that matrix MZ, you have 2D columns, and you can interpret them as, if you want, as coherent states within HD, because that relation is precisely the resolution of the identity in disguise. So the formalism that about semi-unitary matrices is in some sense coherent states in disguise. This is the resolution of the identity, and then there is a group theory there which maps, which if you act on one, you get the other states and so on. I won't go too much into this because I realize the time goes fast. But then you have, you can introduce something which I call Z-Barman representation. Z is a constant, where that vector U, which is a D tuple, is mapped to a 2D tuple from the small space in map to the big space, and that map preserves the product. And of course, not every 2D tuple is the Z-Barman representation of something in HD. You have extra vectors there which are in the external space. And you can do the same with matrices. And I'm saying this because I will use density matrices in a minute. And then, I go a bit fast with this. I'm coming to probability currents when you have a density matrix in the full universe, and that H2D evolves unitarily with some Hamiltonian there. But then, when you go to the projection in the smaller space, you have a probability current, which is the projector to the small space like this, and this is it's minus if you project to the outside space. So, this is the probability current from my system to the external world, and if you put this into this, you prove another relation for the probability current, which is like this. This is the derivatives, and you can write a Taylor series like this. And here, I won't go into this a lot, but here I have an example of what I showed that you get numbers. So I come now how to connect the Grothendieck Q, how to use this as a figure of merit for open systems. First result is that unitary transformations in the full universe are projected to the scaling transformations in the open system, in the smaller system. The second is that there is an interesting link between the probability currents and the Grothendieck Q, which is this. And if this is, doesn't vary a lot with time, then the derivative of that Q is equal to the probability current with this constants there. So the derivative of that Grothendieck Q that I said, this is my first result, is equal to the probability current. Example with Q greater than 1, I take this matrix, density matrix now 1 over D times 1. It's an important density matrix in the small system. And when I go in the big system, it becomes that projector there. And then I choose this example with these matrices, and I get that this Q is greater than 1. So I have an example, and then the last bit is I compare that Q in an isolated system with the corresponding quantities in an open system. And for that example, as I said, this one in an isolated system, it gives Q less than 1 in an isolated system. And for any matrix B and W, the derivative of this is 0, and the probability current is 0. In the open system, that Q is greater than 1, and the time derivative is greater than 1, and the probability current is non-zero. So, as I said earlier, all pure states and some mixed states in an isolated system give Q less than 1, and that's why I looked at the open systems. The question is, can you get Q greater than 1 I mean, do you get Q greater than 1 only in open system, or there are some Q greater than 1 in an isolated system? And I don't know the answer to this. So what I did is I used direct sum formulas for an open system. Most existing work uses the tensor product, where the HD is embedded into a bigger system, H2D, the full universe. And there I calculated some probability currents in the open system to the external well, and I showed that this Grothendieck Q is related to this probability current. If you don't like to think the external world is a very abstract concept, you might think that you have your system, another system there, and there are very high potentials here in the middle. So classically, they cannot communicate, but they communicate through quantum tunneling, which is the first thing that you learn when you do quantum mechanics. And so you might want to interpret that external system as another system which communicates with my system only through tunneling because of very high potentials in the middle. And it also worked, although I haven't done all the details, to take, in this semi-unitary matrix, I have it was d times 2d, you can take d times 3d, you have three systems which communicate through tunneling and so on. So this is something that I need to work out a bit better the details. Thank you very much indeed.